Imagine 3 points suspended in space, positioned so they don't form a single straight line. Connect them, and you have a triangle. When we move that shape onto a Cartesian plane, those 3 points become defined vertices, A, B, and C, anchored in a two-dimensional coordinate system. From here, the immediate instinct is to use the standard Euclidean formula. Area equals 1/2 the base multiplied by the height. But finding that height requires measuring a true perpendicular line down to a slanted base. Because the base isn't aligned with our grid, calculating that specific distance using raw coordinates becomes a difficult multi-step process. To compute the area efficiently, we need to stop trying to measure the internal space of the triangle and find an approach that uses the coordinate system itself. Instead of working inside the triangle, we can look outward and leverage the x and y axes. The solution lies in creating bounding shapes, geometric forms that enclose the triangle but are easier to measure against a flat grid. By projecting the vertices directly downwards to the x-axis, we anchor the triangle to the rigid logic of the coordinate system. These projection lines form vertical segments, running perfectly parallel to the y-axis. These new boundaries create specific geometric shapes known as trapeziums. Unlike a slanted triangle, a trapezium mapped this way has parallel vertical sides and a flat horizontal base, meaning its area can be calculated using only vertical and horizontal grid measurements. Finding the area of the triangle now becomes a process of calculating the area of the space surrounding it on the axes. Let's focus on vertex A, defined by the general coordinates x1, y1. We drop a perpendicular line from vertex A directly to the horizontal x-axis. This point of intersection is point D. Because point D rests on the horizontal axis, its vertical elevation is 0, so coordinates for D are x1, 0. Applying this projection to vertex B gives us point E at x2, 0, and projecting C downwards creates point F at x3, 0. The free-floating spatial vertices are now anchored as horizontal reference points on the x-axis. These projection lines have created an overarching polygon spanning from A down to D, across to F, and up to C. Because the outer vertical sides are parallel, this entire shape is one large trapezium, ADFC. Triangle ABC is contained within this boundary. To isolate the triangle, we account for excess space. Flanking left is trapezium ADEB. Flanking right is the second excess block, trapezium BEFC. To find the area of the triangle, we simply calculate the total overarching area and subtract the excess from both sides. We can write this as a structural equation, starting with the area of the large trapezium ADFC. We subtract the area of the left side trapezium, ADEB. Then we subtract the area of the right side trapezium, BEFC. This geometric subtraction provides the blueprint needed to build a coordinate-based formula. The standard formula for the area of a trapezium is 1/2 times the sum of the parallel sides multiplied by the height. We apply this formula to our largest bounding figure, trapezium ADFC. The parallel sides of this trapezium are segments AD and CF. Since point D is on the x-axis, side AD's length equals the y-coordinate of vertex A, or y1. Similarly, side CF's length equals the y-coordinate of vertex C, or y3. The horizontal base, segment DF, serves as the height because it is perpendicular to the vertical sides. DF's length is the difference between the x-coordinates, x3 minus x1. Substituting these values into the formula creates the first algebraic term. We repeat this exact process, substituting coordinates for line lengths for the two smaller trapeziums we are subtracting. Substituting all three shapes yields a single algebraic equation based entirely on x and y inputs. If we expand these expressions, multiplying the coordinate sums by the differences in x, we can group the terms and see that much of the algebraic bulk cancels out. This leaves us with a condensed coordinate formula that calculates the area of any triangle without needing to measure heights or angles. Running real numerical data through this framework outputs accurate square unit measurements every time. This formula has one critical operational constraint. It depends on the order in which you input the vertices. The formula is mathematically designed to process the vertices in an anticlockwise direction. If you input the points clockwise, the calculation will result in a negative value. To account for this, We add absolute value notation to the formula. Applying absolute value bars ensures the area remains a positive number, regardless of which way the points are ordered. We began with spatial measurements that were difficult to calculate directly on a coordinate grid. By projecting the triangle onto the x-axis, we replaced the need for physical measurements with a method that calculates area using nothing but the coordinates themselves.